All right, so we're going to take a look at chemistry, and I wanted to go through pretty quickly for you guys for those for whom this is just a review. So without further ado, we're going to go through atomic structure and then how that relates to chemical bonding and how that relates to chemical reactions, and then a brief introduction on chemical reactions, although a good bit of it will be in later units. So let's start out with the most obvious here, which is the definition of matter is any substance that has mass and takes up space, which is a pretty easy concept. Really, everything is matter or energy, which isn't matter. So matter is anything made out of atoms, and hopefully you're pretty familiar with atomic structure, but if you are not, here's a sweet, sweet picture of an atom, and we can kind of look at it in two distinct areas. We can take a look at what's in the nucleus and what's in this area around the nucleus, called either the electron cloud or the orbitals, depending on kind of what textbook you're using, but they're used interchangeably. Sometimes you'll hear like electron shells. So all of those are interchangeable. So let's take a second, and this is really where you'll want to pause me if you need to write anything down. So let's start by looking at the nucleus, which is that center portion. Don't confuse it with the nucleus of a cell. Way different scale, okay? The nucleus of an atom is super duper dense, and the reason for that is because it is made out of protons and neutrons. Protons are positively charged, and they have a mass of 1 AMU, atomic mass unit, as do the neutrons, but they're going to be neutral instead of positive. So both of those are shoved into the nucleus, and they're really, really tightly packed in together, and that's going to make the nucleus really, really dense as compared to the electrons, which are hanging out in this electron cloud, and they're really, really light, 1,000th of an AMU, actually less than that. So we're just going to say that they've got a negligible mass because it is matter. It does have mass, just not a ton of it. So in talking about these different parts, we can start to make sense of the chemistry of it based on how many protons, neutrons, and electrons there are. So let's start by looking at the protons. Protons are going to be what define what element that you're looking at. So every element has a different number of protons. If you add or subtract protons from a given atom, then you're changing the element. So certain types of radioactive decay will do that, and it used to be thought like, hey, maybe we could make gold. No, but idea is still there. If you're looking at the number of protons, then you're looking at the atomic number, which is going to tell you what element that you are looking at. For example, carbon. Anytime you take a look at carbon, you know that it is going to be 6 protons, 6 neutrons. Don't worry about the neutrons yet, but 6 protons, and therefore the atomic number is 6. And anytime you've got 6, it is also carbon. Okay. And the protons have a mass of 1, as do the neutrons, but you don't have to have the same number of protons as you do neutrons. There's quite a few elements that pretty typically have a different number, and some of them are pretty typical to have the same number, and sometimes it's pretty split. So if you have the same element, but you have atoms that have differing numbers of protons and neutrons, let me rephrase that, differing numbers of neutrons. For example, if I'm looking at carbon, most of the time, carbon has 6 neutrons, but sometimes it has 7. We call those different varieties of the same element isotopes. And isotopes, in addition to having a different number of neutrons, also have a different mass because neutrons have mass. Okay, so when we talk about carbon-12 would be a carbon with 12 protons and 12 neutrons. When we talk about carbon-13, it's going to have 12 protons because it has to, because it's carbon, and that's how it's defined, but it's going to have 7 neutrons, okay? So those are isotopes. I'm just making sure that I have everything that I want to say. So you're going to hear mass kind of looked in different ways. So an individual atom can have differing masses. So like I said, carbon-12 and carbon-13. But if we take a look on a periodic table, what we're going to see is we've got this relative atomic mass that can kind of fluctuate, and that is taking into account all of the different isotopes and the ratios in which they exist. So most of the time carbon is at 12, but you can see that about 11% of the time it's carbon 13. I'm oversimplifying, there's some other isotopes in there, but that means that on average carbon does weigh more per mole than just 12, as if it was completely entirely made out of the carbon-12 isotope of carbon. Okay? All right, so protons, positive, neutrons, neutral, and the electrons are going to negate or cancel out the charge of the protons. So if I'm looking at a proton that has a positive charge and an electron that has a negative charge, then they're going to cancel each other out. So anytime you have an element or an atom that has the same number of protons as it does electrons, that is going to be considered neutral. Do not confuse neutral with stable. They're not the same thing. Neutral just means there's no electrical charge to them. But there can still be a lot of chemical reactivity, as we shall see. And so electrons are going to determine the overall charge, because you're kind of stuck with the number of protons that you have, but you can gain or lose electrons. And when you gain a negative charge, that's going to make the atom more negative. And when you lose an electron, that's going to make it less negative. In other words, give it an overall positive charge. So that's where you have the formation of ions. So the addition of an electron is going to make an atom more negative, and that is called an anion. On the flip side, if you lose electrons, that is going to cause the atom to become positive. Fewer negative charges, more positive, and we call that a cation. Okay. Some other just general properties. If we're looking at this periodic table, the different rows are each going to typically contain the same number of electrons in the outer shell in a neutral atom. And that's really convenient because we can say that there's certain properties of oxygen that are going to be in common with sulfur. There's certain properties of lithium that is going to be in common with sodium. So that's the periodic table. And so speaking of it, what's really great about biology is we don't really care too much about what goes on below this line right here. So we can really simplify some rules. So let's talk about what you're going to have the most of in you. Carbon, hydrogen, oxygen, nitrogen, in that order, make up 96% of your body mass, your dry mass. You have about 70-75%-ish of living organisms are made out of water, and that is going to be a big topic moving forward. That's a whole day's worth of stuff right there. So of the not water portion, carbon, that's going to make up the kind of backbone to most of the molecules that you have in your body. Hydrogen, oxygen, nitrogen, followed closely with phosphorus and sulfur are in there too. So sometimes it's helpful to remember CHON or CHONPS, CHONPS. We also have trace amounts of sodium, potassium, calcium, magnesium, iron, and chloride. You will want to make sure to be pretty familiar with those. And if you don't already know the abbreviations or the symbols for them, certainly make sure to have those there. Now, an important thing that is worth mentioning is what these different guys do and where we get them from. Because if we don't have adequate amounts of particular elements, then we can't function. And why is that? And a big part of that has to do with being able to build these really big macromolecules that we'll be talking about later next week, at the beginning of next week. So carbon is the basis of those molecules that make up a huge portion of our bodies. And where do we get carbon from? Well, we get carbon from eating, but we're not special. Actually, what makes trees really special and other autotroph just means someone that can capture their own carbon, is that they can capture carbon just from the air. They don't have to ingest it. So they can use carbon that is a lot more readily available and put it into what is called an organic form that then the rest of life on Earth is going to be relying on. So carbon, we've got this really intricate cycle that happens between all living organisms, and taking the carbon and kind of going back and forth with where that is, kind of cycling it through. So, for example, I take in carbon when I eat sugars or eat any foods And my body's going to break those down, and whatever is not incorporated into my body is then released back into the environment where autotrophs can recapture them. Okay. Same thing is going to be true for nitrogen and phosphorus. We have really complex cycles that we'll be looking a lot at later. Just know that there's cycles that are involved in converting between forms that are usable to animals and forms that are usable to other organisms on Earth. Nitrogen, we're going to see, is going to be really important for both our proteins. So not enough nitrogen, you're not going to be able to make proteins. And it's also going to be important in our DNA and other nucleic acids. Phosphorus, we're going to see a lot in a molecule called ATP. And then sulfur, sodium, iron, we use for all kinds of parts of our body. It's not necessary right now to necessarily memorize them. That was really redundant, but moving on. Okay. Now, when it comes to chemistry, so much chemistry is just dependent on electron behavior. And that's a nice thing about bio, is that we worry very little about things like isotopes and radioactivity. Most of our important information relating to chemistry is actually having to do with the electrons. And so it's important to understand how electrons behave. And they move in these completely random motions, but it's somewhat predictable, and you can get into like the S and the P and the, orbitals. Okay? Think of each orbital as a shell that's further and further from the nucleus, that positively charged nucleus. And so the only reason the electrons are sticking around is because of the fact that the nucleus is positive, and we know that positive and negative will attract. Why does that matter? Well, the electrons that are closest to the center are going to be kind of the most relaxed. They're in a happy energy state. They're not too far from that nucleus, so they're all the way down. But you can't have too many shoved in that area because negatives repel from one another. So as it turns out, we can only get 2 electrons in that lowest shell, or in that lowest energy state. Once you've got more than 2 electrons in a particular atom, then they're going to start filling out subsequent electron shells. So we need to know that there's going to be 2 electrons in the first shell, 8 in the second, 8 in the third, and going back to our periodic table, what that really means is that we are looking at all of these things here in the first 3 rows. Everything below that, biologists don't have to really deal with, which is awesome. Okay, so 2, 8, 8. That's our rule of octet. 2, 8, 8. Past that, don't worry about it. Okay. If you take an atom and you infuse it with a whole bunch of energy, what can happen is those electrons can bounce up to a higher energy state and then fall back down to the lower shell. We're not going to get too much into that yet, but it's nice to file that away so next time when I say it, you're like, oh yeah, I remember Ms. Unger said that. Maybe. Okay. And so why do we care so much about the behavior of the electrons? Is because the behavior of electrons dictates the behavior of the atom, which determines what molecules it will and won't form, or in other words, what partnerships it'll have with other atoms or not. And that has everything to do with chemical reactions and all of the metabolism-y stuff that we're going to be talking about. So, electrons, they're kind of important. So if you've got an atom and the outermost shell, the one on the outside, whether that's the first shell, or the second or the third, as long as they are filled subsequently, so the first one is completely filled before you go to fill the second one. The one on the outside is called the valence electron shell or the valence shell. Now, if that's full, you've got a happy atom. Everything's good, it is stable, and if the protons and neutrons are the same number, then it is also neutral. Now, the only guys that are going to be doing that are these noble gases over here. Otherwise, all chemicals are going to have some level of reactivity based on the fact that they are not completely neutral and stable at the same time unless they are bonded with another atom, okay? So not full, not stable, 2 in the first, 8 in the second and third. So we can look at really, for right now, 3 kinds of chemical bonds, okay? And I think it's really easy to kind of say it's either covalent or ionic. Think of it more as a spectrum, right? Okay, my screen is backwards, so this one. Okay, so on the one extreme, you've got a situation where valence electrons are being perfectly shared, nice and equally, between two atoms. Okay? Think of kids that do a really nice job sharing. It's yours, it's mine, I don't care, we're fine. Okay? That's going to be a covalent bond, and where it's equally shared, we're going to say that that is a non-polar covalent bond. Okay? Think hydrogen. Hydrogen nuclei pull on electrons the same amount as other hydrogen nuclei. So when you have two hydrogens kind of doing a tug of war on the electrons, it ends up getting shared really equally, and that's nice, right? And then we start to get more and more selfish partners involved in a chemical bond. So we could have something like oxygen. And oxygen's really, really electronegative. That means it sucks the electrons towards it. It's really attracting them there. So if you have a hydrogen that is like, okay, yeah, sure, I'll pull a little, and an oxygen that's like, gimme, 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 what you're going to end up with is a covalent bond. They're still going to share them, but not equally, right? Instead of a nice partnership, you've got oxygen yanking at the electrons a little bit more. We're going to call that a polar covalent bond. So there's two types of bonds so far. A nonpolar covalent, equal sharing. A polar covalent, they're sharing, but like the electrons tend to be towards the one that is more electronegative. Or you can have a situation where one element or one atom straight up like yoinks an electron away from another. And why would they do this? A lot of times it has to do with another atom becoming more stable by losing electrons. So let's say, for example, you have sodium. Sodium is going to be in the leftmost column on the periodic table, and those guys over there want to get rid of one electron. And the reason is their valence shell has one. So to fill the valence shell, they would either need 7 more, except for hydrogen, but everyone else, 7 more, or they would just need to get rid of 1 electron. By getting rid of 1 electron, you now don't even have that shell, and their valence shell becomes the one just inside of that. That means now that shell is full, it's stable. And as a consequence of that, as I said earlier, when you lose 1 electron, you become positively charged, right? Sodium right here, the loss of this electron, that negative charge, is going to cause the sodium to become positive. And that is called a cation, a positively charged ion. And that guy is going to become attracted to anything that's negatively charged. So chlorine, where it's got 7 in its outer shell, is going to want 1 more. And I just realized this is only showing 6. What a horrible picture. Anyway, so chlorine will have 8 in its outer shell. Sodium will have 8 in its outer shell. So now they're both stable. But the chlorine is going to have an overall negative charge from having picked up an electron from somewhere, maybe pulling it away from a sodium atom, but most of the time those aren't just sitting around because they're so unstable. And then the sodium is going to have a negative charge from having, positive charge from having lost one of the electrons. So that positive and that negative of the sodium and the chlorine, they're going to be like, hey, I like you, positive, negative, and attract. And that is called an ionic bond. And that kind of bond is really just the extreme version of a polar covalent bond, because now you've got this chemical activity where there's not necessarily electrons being shared between them, but that transfer of electrons has meant that one of the atoms is really, really charged, right? A complete positive or negative charge that allows them to still hook on to each other and become attracted, okay? All right, so why do we care about all of this? Is because how electrons behave is going to be completely indicative of the chemical reactions that then occur. So if you have 2 stable atoms, they're not going to react. And no reaction means no metabolism, and that means no life. So metabolism is all about the different chemical reactions. Going back to the conversation about carbon from earlier, as a heterotroph, meaning an organism that has to, an organism that has to take in nutrients, I also am going to be using those nutrients to get energy. And so when I have chemical reactions that happen in my body, what's going to be happening each time is when the chemical bonds break, energy is released. Okay, so I want you to think about electrons and especially covalent bonds as a form of stored energy. Anytime covalent bonds break, energy can be released, and that energy can be coupled to do other things like wake my sorry butt up at 5:30 in the morning and make this video. Then, on the flip side of that, anytime you need to build up molecules, meaning building more covalent bonds or building more chemical bonds, that is going to mean that complexity is added and more energy gets put into that molecule. So that's going to require the taking in of energy. All of that is to say, we'll get there. Don't freak out if you were just like, what is she talking about with energy? Okay. Big picture here is that this constant break form of all these different chemical bonds, that is the basis of your metabolism. Okay. I'll talk about redox reactions at a later date, but that does leave us with the final kind of topic here, which are chemical reactions. So this was one of the quizzy questions that you had yesterday, or the pretest questions. And if you have methane, CH4, and oxygen, when whatever reaction happens, it has to make sure that you still have the same number of atoms when you're done, or the same overall mass, the same things that you start with, you have to end with. Nothing just disappears. And so if I've got methane, which is CH4, that means 1 carbon and 4 hydrogens. Then this 1 carbon and 4 hydrogens needs to be found somewhere in our products. So reactants on the left are what go into a chemical reaction to form products that are written on the right. Okay, so CH4, methane, is 1 carbon, 4 hydrogen. Here I've got 2 oxygen, this right here indicating that I have 2 of the molecule, and then O2 the molecule, meaning that there are 2 atoms of each oxygen present. Okay, all right, so start with 1 carbon, 4 hydrogen, have to end with 1 carbon, 1, 2, 3, 4 hydrogen, and then the 4 oxygen that are 4 oxygen atoms that are coming from the molecular oxygen are going to then be found in carbon dioxide and water. And how would you have known that? Well, the options included like calcium carbide. There's no calcium in the reactants, so it can't be in the product. I don't remember what the other answers were, but you know that if you start with carbon somewhere, you have to make sure that you end with it somewhere. So reactants and products, and keep in mind that chemical reactions can happen in both directions. Those are reversible, and eventually you get to that equilibrium point where you have the same amount of movement towards this side of the equation as what is going in the opposite. Okay, with that, if you've got any questions, let me know. Otherwise, I hope this helped.